Okay, so I want to show you some different ways of doing the same thing in Maple. The point being to give you an introduction to various ways of writing programs in Maple, but also to open your eyes to the important fact that sometimes it's very different programs that make the best solution to the same problem, and it sort of depends on the whole context of the thing that you're trying to do. What is a good solution to a problem that you're trying to solve in Maple? So the idea of this example is to just show you the same thing 3 times, actually 4 times, because there's a built-in way of doing it in Maple. So the problem that I'm trying to solve is to compute the power set of a given set. That is the set of subsets of the given set. This is built into Maple in the CombiNet package, and you can see Maple computes the power set of ABCD like this. And of course, it's important to note from the outset that the number of elements here is 2 to the 4, that is 16, because we have 4 choices. Either A is in or it's not in, either B is in or it's not in, either C is in or it's not in, either D is in or it's not in. And for all the programs that I'm going to show you, that will be very clear that we sort of have to make this choice. So the first version I have here is you see it twice, once in red and once in blue. So when I evaluate this in Maple, it will write it back to me. But let's focus on the red version. So what is this? So this is supposed to be a program that computes the power set of the set M. And the way it works is that it starts by letting G equal the set containing the empty set. So we start with the set equal the set containing the empty set. And you can see at the end of this program, I'm planning to return G. So I'm planning to return G, which is going to be my list of my set of sets. But the point is now that if I have some elements in M, which I most likely will, then I'm going to say, well, for these elements in M, I will take the sets that I already have, and I will add the element to it, and I will also not add the element to it, and I will take the union of these two sets and keep going. So the way this is working is that I start out with G equals the empty set, right? So I will have the empty set like up here. Now I take the first element in the set M given, that's A, and then I create the element, the set of sets where I've added A to all the sets that I already had. So I had the set, the empty set, and I added A to that. That gives me A. And so when I've done the inner for loop here, I will have created the list of sets containing one set, namely the set with A in it. So the way this works is that I run through the elements in G, the sets that I already have, and then I add that to my list here, my temp G list. So that's a temporary list of sets, and I add the set with E added to it from the original list. So let me do this once more. So when I've done it the first time, I will have these two sets, the empty set and the set containing A. Now I'm doing this with B, and the way this is going to work is that I take these elements here, 0, the empty set, and A, and I add B to it. So I add B to the empty set, that gives me B. I add B to the set A, that gives me AB. That gives me two sets, and I take the union with the sets that I already had, the empty set and A. So when I've done this the second time, I will have 4 sets, empty set A, B, AB. Right? So this is how this works, and then I keep on doing this. So the key operation is down here. So I keep, you see, I let G equals the union of G with temp G. So G is the sets that I already have, and then temp G is a new copy of the sets that I already had with the new element added in. Okay, so this is the idea of power set 1. How about power set 2? Well, the next program I'm going to show you is going to be recursive. And it has the same basic idea as the one that I just showed you, but it's recursive in the sense that my program calls itself. So you can see pset2 calls pset2 down here. So that's what recursivity is about. You have a program that calls itself. So the idea is that I'm saying, suppose that I know how to compute the power set of a small set. Then how can I compute the power set of a slightly bigger set? Well, I can take one element and I can, out of the slightly bigger set, and I can add that to the ones I already have, and I cannot add that to the ones that I already have. So the basic part of my procedure is what happens down here, right? So the idea is that to compute the power set of M, I will compute the power set of M where I've removed the element E, but where my G now has the original G's and all the sets where I've added E in. So that's exactly the same thing that I did before, but I've coded it in a recursive way with my program calling itself. And of course, when we make recursive programs, we need to be really careful because a recursive program has to start somewhere, right? So if you, I mean, for instance, computing n factorial, we can think of this recursively. We'll say that n factorial is n times n minus 1 factorial. But then when you sort of trace back, you need to start somewhere. Usually you would say that 0 factorial was 1, for instance, right? And that's what I also need to do here. So I need to start my recursive program, and that's the base case that I need to do first. And that's exactly what I had here. So suppose that my set that I'm adding on with the set that's called M, suppose that's empty. I will say if the number of elements in it is 0. Then I'm not going to change G. Right? So that's the idea. So you see my recursive program works in this following way, that if M is empty, I keep G. If M is not empty, I remove one of the elements in M, and I call the program itself, not with G, but with a copy of G and another copy of G where I added the elements in. So it's exactly the same idea as before, but now to use it, I need to call it in the correct way. So if I want to compute the power set of M, I will do it by calling recursively pset2 with M and the set containing the empty set. So my base case will trace me all the way back to the set containing the empty set, and that's exactly like what I had before. So these two kinds of approaches are philosophically the same, but they're coded in a different way. One is iterative with some for loops inside each other, as you can see here, and the other one is recursive, the program calling itself. And which one is better? Well, that depends a lot on what you're trying to do. Right? If you're trying to do something that fits well with the recursive procedure, then that might be better. If you're trying to do something that fits well with the iterative procedure, maybe that's better. But there's a third way of doing that I think would most of the time be superior to the other two in doing experiments, and that's somehow enumerating the elements of the power set. So we already know from the outset how many elements there's going to be in the power set because it's 2 to the n, where n is the number of elements that I already have given. So a way of now doing this is to say, well, if I know the number of elements in the power set, let's give my elements in the power set numbers. And the idea for doing this would be to say, well, let's think of the numbers as binary numbers. Because when I'm thinking of them as binary numbers, I will have some zeros and some ones. And if I have a 0, I will say, well, that means that the element in my original set corresponding to that entry is not part of the power set. And when I have a 1, it becomes part of the power set. So I have this little procedure here that's called extract elements 3. And the way it works is that it takes a number, it's like a good old non-negative number, and creates a set by looking at the digits of that number expanded in binary. So I'm using a built-in procedure called split to get this behavior. Split works the way that it takes a number like 11 and writes it up in binary as a list. So it's supposed to be read like this. So These down here, these are the 1s of my binary numbers. These are the 2s and the 4s and the 8s. So 11 I get out as sorry, I did this wrong. These are the 1s, these are the 2s, these are the 4s, these are 8s. So 11 I get out by 8 plus 2 plus 1. Right? But the thing is that now I have this little list of 1s and 0s, and then I will say, well, because I have a 1 here, this is how my program works. Because I have a 1 here, I've extracted the A. Because I have a 1 here, I've extracted the B. Because I have a C here, I'm not extracting the C. Sorry, because I have a 0 here, I'm not extracting the C. Because I have a 1 here, I am extracting the D. Right? So the idea with extract elements is that you get a number. This has to be between 0 and 15 in my setting here, or more generally, if I have n elements in my original set, it has to be between 0 and 2 to the n minus 1, because then I have a binary number with that length. And then I just use the 1s and 0s to decide what is in and what is out. So this works the way that it sort of goes through the digits and in created by split. And then if there's a 1, I put the element in. And if there's not a 1, I don't do anything. So that's how this works. And then my power set 3 will work the following way. It just runs through all the numbers from 0 to 2 to the m minus 1, and then creates that subset and collects everything in a big set. Right? So you can see this is a very different approach. I somehow decided on a way of enumerating the elements that I'm looking at, and then now they have numbers between 0 and 15, and then I just ask for element number 0, 1, 2, 3, and so on. Right? So this is one advantage of this is that it's now very easy when you're doing experiments to talk about various subsets because they have numbers, right? So I can sort of say, well, something interesting happens at 11 or whatever. So sometimes this is a useful way of doing this. So so of course we need to convince ourselves that these programs work, and you can sort of see that they at least they seem to do the right thing. One final thing I would like to point out is that they are not equally efficient, right? So which one is better depends a little bit on what you're trying to do. I mean, if you sort of have to go in to the computation of power sets and sort of see this, you have to be, maybe 1 is better than 3 or vice versa. But of course, one important property of these programs is how fast they are. And then you can't really beat the built-in one. So the built-in one can finish in a 20th of a second, whereas my first one, which was the one with the 2 for loops inside each other, takes a very long time to complete, something like 10 seconds. The one with the recursive definition is actually okay fast, not more than twice as much as the built-in one. And then the last one, which had the built-in enumeration, takes about 10 times as the other one, right? So of course, it depends a little bit on the context, how important it is for this to be fast. Also, how big do you want to go? I went to 15 here. But so I can imagine situations where all of these choices may be the optimal choice. It depends a lot on what we're trying to do besides what the power set computation in itself.